Welcome to MindTier Learning, where GCSE Geography is made simple. In this presentation, we'll explore effective strategies and tips to help you succeed in your GCSE exams. Whether you're just starting your revision or looking for ways to improve your study habits, this guide will make the process more manageable and less stressful. Let's dive in and make your learning journey straightforward and successful. Today's lesson is on weathering and mass movement. In this lesson, we are going to look at the subaerial processes that shape our coastlines. Subaerial processes are processes that happen on the land surface, rather than directly in the sea. They include weathering and mass movement. When we study coasts, it is easy to focus only on waves. Waves are very important because they attack the base of cliffs through erosion. But cliffs are also attacked from above by the atmosphere, rainfall, temperature change, plants, and gravity. So today's lesson is about the forces acting on a cliff from above. Weathering weakens the cliff. Mass movement moves weakened material downhill. Marine erosion then removes material from the base. Together, these processes explain why coastlines are constantly changing. The big question for today is, how do weathering and mass movement make coastlines unstable? Let's begin with today's learning objectives. By the end of this lesson, you should be able to do 3 things. First, you should be able to describe mechanical, chemical, and biological weathering processes. Mechanical weathering breaks rock apart physically. Chemical weathering changes or dissolves rock through chemical reactions. Biological weathering happens when living things, such as plant roots or animals, break down rock. Second, you should be able to explain how different types of mass movement occur on cliffs. This includes rockfalls, landslides, and rotational slumping. Third, you should be able to analyze the link between climate change and coastal instability. Climate change can increase storm frequency and rainfall intensity. This means cliffs may be attacked more strongly from below by waves and from above by rainwater and weathering. So today we are not just learning definitions. We are linking processes together to explain coastal retreat. Before we go further, let's go through the key vocabulary. The first word is weathering. Weathering is the breaking down of rocks in situ by the atmosphere. In situ means in place. So weathering weakens rock where it is, rather than transporting it away. The second term is subaerial. Subaerial processes are processes that happen on the land surface. At the coast, the main subaerial processes are weathering and mass movement. The third word is permeability. Permeability means how easily water passes through a rock's pores, cracks, or joints. Permeable rock allows water to pass through. Impermeable rock does not. The fourth word is slumping. Slumping is a form of mass movement where material moves down a curved surface. It is especially common when cliff material becomes saturated with water. These terms are important because they help us explain why some cliffs collapse suddenly while others retreat more slowly. Before we focus on the land, let's recap the role of the sea. Destructive waves are high-energy waves. They usually have a high frequency and a strong backwash. This strong backwash removes sediment from the beach and can expose the cliff base to more direct wave attack. Destructive waves can erode the base of cliffs through hydraulic action, abrasion, and other marine erosion processes. But now we need to ask, what happens when the cliff is attacked from above as well as below? From below, waves undercut the cliff. From above, weathering weakens the rock. Gravity then pulls weakened material downwards through mass movement. This combination makes coastal cliffs unstable. So in this lesson, we are adding another part of the coastal system: the atmosphere, rainfall, temperature, and gravity. Let's do a quick recall check on wave types. Question 1. Which wave type has a stronger swash than backwash? Question 2. Does a large fetch result in higher or lower wave energy? Question 3. What is the primary factor determining wave power besides fetch? Take a moment to think. Remember, swash is the movement of water up the beach. Backwash is the movement of water back down the beach. Fetch is the distance of open water that the wind has blown across. Let's go through the answers. For question 1, the answer is constructive waves. Constructive waves have a stronger swash than backwash, so they tend to deposit material and build beaches. For question 2, a large fetch results in higher wave energy. If wind travels over a long distance of open water, it has more time and space to transfer energy to the sea surface. For question 3, The primary factor determining wave power besides fetch is wind strength, although wind duration is also important. Stronger winds and longer-lasting winds create more powerful waves. This matters because wave energy affects how strongly the sea attacks the cliff base, while weathering and mass movement affect the cliff from above. Now let's look at the first type of weathering, mechanical weathering. Mechanical weathering breaks rock apart physically without changing its chemical composition. One important example is freeze-thaw weathering. Freeze-thaw happens when water enters cracks in rock. If the temperature falls below freezing, the water turns to ice. When water freezes, it expands by about 9%. This expansion puts pressure on the surrounding rock. When the temperature rises again, the ice melts and the pressure is released. If this freezing and thawing happens repeatedly, the crack becomes wider and wider. Eventually, pieces of rock can break away. Freeze-thaw weathering is most effective in places where temperatures regularly rise above and fall below 0 degrees Celsius. This is why the process is common in cold or upland environments, and it can also affect exposed coastal cliffs during colder weather. The key idea is, freeze-thaw weakens cliffs by widening cracks over time. Another type of mechanical weathering is salt crystallization, sometimes called salt weathering. This is especially important in coastal environments. Sea spray carries salty water onto cliffs and rocks. That salty water enters small pores, cracks, and joints in the rock. When the water evaporates, salt crystals are left behind. As the crystals grow, they expand and push against the rock from inside the cracks and pores. Over time, this pressure can break the rock apart. Salt crystallization can create a rough, pitted, or honeycomb appearance on cliff faces. This process is common in warm coastal areas where evaporation is strong, but it can also occur anywhere sea spray repeatedly wets rock and then dries. So, like freeze-thaw, salt crystallization is a physical process. It does not dissolve the rock chemically. It breaks it apart by pressure from inside. Now let's look at chemical and biological weathering. Chemical weathering happens when rock is changed or dissolved by chemical reactions. A key example is carbonation. Rainwater mixes with carbon dioxide in the air to form weak carbonic acid. This weak acid can dissolve rocks that contain calcium carbonate, such as limestone and chalk. Over time, carbonation weakens and dissolves these rocks. This is especially important on coastlines made of chalk or limestone. Biological weathering happens when living things break down rock. One example is root action. Plant roots grow into small cracks in the cliff. As the roots grow thicker, they force the cracks wider. Animals can also contribute. Seabirds and mollusks may burrow into softer rocks, weakening them further. So cliffs can be weakened by physical processes, chemical reactions, and living organisms. All of these make it easier for waves and gravity to remove material later. Now let's check the different weathering processes. Match each process to its definition. The processes are 1. Freeze-thaw 2. Root action 3. Carbonation 4. Salt growth. The definitions are A. Evaporating seawater, leaving expanding crystals behind. B. Water expanding as it turns to ice in rock fissures. C. Weak acids and rain dissolving calcium carbonate rocks. D. Biological force widening fractures in the cliff face. Take a moment to match them. Think carefully about which are mechanical, which are chemical, and which are biological. Freeze-thaw and salt growth are mechanical. Carbonation is chemical. Root action is biological. Let's go through the answers. Freeze-thaw matches with B. Water expanding as it turns to ice in rock fissures. Root action matches with D. Biological force widening fractures in the cliff face. Carbonation matches with C. Weak acids and rain dissolving calcium carbonate rocks. Salt growth matches with A. Evaporating seawater, leaving expanding crystals behind. A strong GCSE answer should be able to explain these processes, not just name them. For example, freeze-thaw weathering happens when water enters cracks, freezes, expands, and widens the cracks. Repeated cycles eventually break pieces of rock away. That kind of process explanation is what earns marks. Now let's move from weathering to mass movement. Mass movement is the downhill movement of weathered material under the force of gravity. Weathering weakens the cliff. Mass movement moves the weakened material. There are several types. The first is rockfall. A rockfall happens when fragments of rock break away from a steep cliff and fall vertically or near vertically. This often happens after freeze-thaw weathering has widened cracks. The second is a landslide. A landslide happens when blocks of rock or soil slide rapidly down a surface. This may be triggered by heavy rain, undercutting at the cliff base, or weak layers within the cliff. The third is rotational slumping. Rotational slumping happens when saturated material moves down a curved slip surface. The movement is rotational because the material tilts backwards as it slides downwards. This is common on cliffs made of clay because clay can become heavy and slippery when saturated with water. Mass movement can happen suddenly, making it very dangerous for coastal communities and visitors. Now let's look more closely at coastal slumping. Slumping is common where there are layers of different permeability. For example, a cliff may have a permeable layer on top and an impermeable clay layer below. Rainwater infiltrates the permeable top layer. That means it soaks down through the rock or soil. But when the water reaches the impermeable clay, it cannot pass through easily. The water becomes trapped. The clay then becomes saturated. Saturated clay is heavier and weaker. It can also become slippery, reducing friction between particles. Eventually, the weight of the saturated material causes it to move down a curved slip surface. This creates a rotational slump. The slide gives us the key point. Water is the key catalyst for mass movement. It adds weight and reduces friction. This is why heavy rainfall can make coastal cliffs much more unstable. Now let's connect this to climate change. Climate change can accelerate coastal retreat in two main ways. First, increased storm frequency or storm intensity can increase wave attack at the base of cliffs. More powerful waves can increase erosion through hydraulic action and abrasion. This undercuts the cliff base and makes the cliff less stable. Second, heavier rainfall can increase instability from above. More rainfall means more water infiltrates cliff material. If the cliff contains clay or other weak material, this water can increase saturation, add weight, and reduce friction. That makes landslides and rotational slumping more likely. So climate change can attack cliffs from both directions. Waves attack from below. Rainfall and weathering weaken from above. This is why a wetter and stormier climate can make coasts more unstable. Now let's think critically. The question is, if we build sea walls to stop waves from eroding the base of a cliff, will the cliff stop retreating? At first, it might seem like the answer is yes. If waves cannot reach the cliff base, then marine erosion is reduced. But today's lesson shows us that this is not the whole story. Cliffs are not only eroded by waves. They are also weakened by weathering and moved by mass movement. Rainfall can still infiltrate the cliff. Freeze-thaw weathering can still widen cracks. Plant roots can still force fractures open. Saturated material can still slump or slide downhill. So a seawall may reduce erosion from below, but it does not completely stop cliff retreat from above. This is why coastal management must consider the whole cliff system, not just the wave attack zone. You might have said that the cliff may still retreat because of weathering and mass movement. That is correct. You might also have said that rainfall can cause slumping and landslides even if a seawall protects the cliff base. That is a strong point. Freeze-thaw and biological weathering can also continue above the seawall. A strong GCSE answer might say, a seawall can reduce marine erosion by stopping waves from attacking the base of the cliff. However, it will not completely stop cliff retreat because subaerial processes continue. Rainwater can still infiltrate the cliff and cause saturation, increasing the risk of slumping or landslides. Freeze-thaw weathering and root action can also weaken the cliff from above. Therefore, seawalls reduce one cause of erosion but do not remove all causes of coastal retreat. That answer is strong because it recognizes the interaction between marine and subaerial processes. Let's finish by bringing the lesson together. The coast is a battleground between different forces. The sea attacks from below through waves, hydraulic action, abrasion, and other erosion processes. The atmosphere attacks from above through weathering. Rainfall, temperature change, salt spray, chemical reactions, and plant roots all weaken cliff material. Gravity then pulls weakened material downhill through mass movement. This combination ensures that the coastline is never stationary. Even if the sea is calm for a while, the cliff may still be weakening. Even if a sea wall protects the base, the cliff may still be affected by rainfall and slumping. In the next lesson, we will look at how these processes create coastal erosion landforms such as caves, arches, stacks, and stumps. The key idea from today is coastal retreat happens because cliffs are attacked from both above and below. If you found this presentation helpful, don't forget to like the video and subscribe to our channel. Your support helps us create more content that you'll enjoy and learn from. Thank you.